So I will begin with a word of prayer. Once I get up here. Heavenly Father, we thank you for this day. I thank you for this class and this opportunity we have just to meet and study your creation. I pray that you be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. So, we talked about a matrix again as kind of just a notation to avoid writing a whole system of equations, right? Just a sort of a shorthand for elementary row operations which correspond to like rearranging a system of equations, linear equations, so that the solution set doesn't change, right? But we can think of the matrix on its own, right? And so today I'm going to describe that for you, what you might call matrix arithmetic. And so the chief thing here is the notion of equality. If A and B are both in, let's say, Rm by n, then A is equal to B if and only if Aij is equal to Bji for all 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to n. So I'm throwing a bunch of notation at you here, but we need to kind of, get on the same page about what these words mean. So let's talk about it. First of all, my Rm by n, all that means, right, this thing here, this is the set of all m by n matrices with entries in the real numbers, right? And I'm saying that two matrices are only equal if they have the same size, right? And they match, every component has to match. So, for example, if I had, x 3, 2, 7 equals to 10, 3, 2, 7, this forces what? X equal to what? 10, right. So these two matrices are only equal if every component matches. So we can equate coefficients of matrices. Matching components have to match, right? That's the first thing. M is the number of rows, right? M rows, n columns. Let's talk a little bit more about that. So if I write A equals to, say, A11, A12, A21, A22, and then so forth and so on, all the way until I get to AM1, AM2, A1n, A2n, AMN. So this is the matrix, right? I can look at different things in this matrix. For example, if I just look at this part, right? This is called column 1 of A. All right? If I was to just look at, say, this part, this would be row 2 of A. All right, so we can talk about rows and columns of a matrix. Like here's the definition. If we talk about the jth column of A and we want to calculate the ith component of that, guess what that's equal to? How do we find the ith component of the jth column? Yeah?
Column J, row I.
Column J, row I. Yes, but what is that in terms of this notation? A what? A sub what? A sub ij, right. For example, like the first component of the first column is A11. The mth component of the first column, AM1. All right? How about if I talk about the ith row of A? and I want to look at the jth component of that. What's that equal to? Aij again, right. Notice that there's an asymmetry here in the way the indices work. You see how that goes? The jth column, if I want to get the ith component, I got to flip the order of the indices over here. That's just how it works. On the other hand, with the row, I have an I here, I have a j here, it's still Aij. Rows and columns are different. All right? Now, we can write A, right, either as a bunch of columns glued together, like column 1 of A, column 2 of A, and so forth and so on, until I get to the nth column of A, right? Or, what else could I do? I can write A as a stack of row vectors. Row 1 of A, row 2 of A, dot, 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 row M of A. You have options in terms of how you look at the matrix. You can either cut it apart into columns or cut it apart into rows. I mean, you could do other things, but notice this is kind of not a very deep comment, but it's a useful comment. Two matrices are equal if they have matching columns. Two matrices are equal if they have matching rows, right? I have defined equality of matrices in terms of matching components, but a corollary to this you could easily see is two matrices would be equal if and only if every, column 1 matches column 1, and column 2 must match column 2, right? Or row 1 has to match row 1, and row 2 has to match row 2. You have to have all matching rows, all matching columns in order to have equality. Sometimes we make like column level arguments, and that's helpful. All right, so yeah. Another thing I should mention, so if A is an Rm by n, then A transpose is an element of R n by m. And our definition is that A transpose Ij is equal to what? What's the definition of transpose? Yep.
You flip it diagonally?
Yeah, but how about the formula here? Like, what do I write here? What's the definition, though? AJI, right. Now, you're right. What that amounts to, in practice, is you flip the entries over the diagonal, and the diagonals stay the same, right? So the diagonal would be like AII. So A transpose II would be equal to AII, which says nothing happens to the diagonals. But, yeah, it's good to have an example. So example 2, let's see what you're talking about. So if I have 1, 2, 3, 4, 5, 6, and I transpose that, I get 1, 2, 3, 4, 5, 6. Now I guess this doesn't quite, you were talking about diagonals, so you're thinking about like a square matrix, right? Because I don't know what the diagonal is for this thing, right? But if I have B, for example, is 1, 2, 3, 4, 5, 6, 7. Yeah, I personally don't define the diagonal for a rectangular matrix. So I don't think we define diagonal for rectangular matrix, but I could be wrong. Let's see here. 1, 2, I don't define it. I can tell you that much. 4, 5, 6. Somebody else, you could define it. You're free to make your own definitions. But understand that I'm going to grade you on mine. Sorry. But there's a transpose of a square matrix. And what you're saying is exactly right. We can envision the transpose as fixing the diagonal, right? And then flipping across the diagonal like that. That is indeed how I think of it. Here's another way to think of it. What the transpose of a matrix does is it takes a given column in the initial matrix and it takes the same entries and makes it to a row of the other matrix. So this is how I actually did this. To find A transpose, I'm like, row 1 is 1, 2, 3. That means column 1 is 1, 2, 3. of the transpose. Row 1 is 4, 5, 6. Oh, okay, so row 2 is 4, 5, 6, so column 2 is 4, 5, 6. So yeah, this is part of like a more general comment, which is that if you want to calculate the ith row of the transpose, it's equal to the ith row of the original matrix. That's how they're related. And if you don't believe me, well, how would we check equality of these two things? These are vectors, right? So vectors just have components. To see if these are equal, we can ask, okay, so I'm looking for column I of A transpose. Like, what's the jth component of that? Is that equal to row I of A, the jth component of that? So the ith row, so this by definition, right, is A transpose Ji. And on the other hand, that by definition of transpose is Aij. But this, of course, is also Aij. So as you can see, woohoo! So it's not an accident. Like, we can show that it's not a quirk of my particular example. This is just generally true. And I like what you said about reflecting across the diagonal, but, you know, there's more than that. So as a point of notation, guys, I need to make something clear. We talk about Rn in here. All right, in Rn, my notation is something like this, x1 through xn, all right? Such that x sub I is a real number, all right? For I equals 1 to n. This is Rn. This notation is a sneaky notation. It's actually a shorthand for a column vector. So when I use parentheses, that's a sneaky, hidden column vector notation. And so this is actually an element of what? This is actually an element of R. How many rows? 1, 2, all the way out, n rows. How many columns? 1. So this is actually an n by 1 matrix. In short, our convention is that Rn is Rn by 1, which is to say that we take column vectors as primary. We think of points as column vectors. This matters because some people take rows as primary and their points are 1 by n vectors, which makes you write formulas different. So I'll try not to do that. We do sometimes work with row vectors, though. It's just inevitable. So just to be clear here, 1, 2, 3 is equal to like 1, 2, 3, which is equal to 1, 2, 3 with the transpose. Okay. If you want to make a row vector into a column vector, put a transpose on it. The original edition of my 221 notes, I just had everywhere, instead of this notation, I had row vectors everywhere with the square brackets and a transpose tacked on them. You might find one somewhere. I tried to get rid of them all in my last edit. All right. Anyway, I'm not saying anything terribly interesting, but it is, you're like, well, this is just notation. Yes, about 50% of this course is just notation. Don't ignore it. Like, that's a lot of what you're trying to learn is notation. Notation is this course, and much of it is notation. It's like, oh, I understand the math. I don't understand notation. Well, then you don't understand the course. The course is notation. Like, don't ignore the notation. All right. So, moving on. If we want to define the sum of two matrices, right? Or a scalar multiple of a matrix, how do you think we should do that? First of all, to add two matrices, they have to be the same size, all right? We can't add matrices of different size, at least not yet. Okay, maybe not ever. So, like, how should I define the sum of two matrices? Remember, if I can define what happens to an arbitrary component, I've defined what happens to the whole thing because we define equality with components. Yep.
Aij plus Bij.
I heard an Aij plus Bij. Anyone care to disagree? I hope not, because that's right. And this is Cij, all right? This is how we define matrix addition, matrix scalar multiplication. If you want, we could define subtraction too. What would that do? Yeah, I mean, in math classes, we almost always define subtraction as like addition by the addition of the, the additive inverse. But if you wanted to be human beings and give a definition for subtraction, you could just do this. It'd be fine. All right. Great. So I'm embarrassed to even do this example in here, but here you go. Example 3. Let's see here. 3, 2, 1 plus 0, 6, 7, 0, 6, 7, 0, 6, 7. There we go. We can add these matrices because they're both 3 by 3, right? And so I get 3, 6, 7, 0, 8, 7, 0, 6, 8, right? There you go. Let's scalar multiply. What happens if I do like, 10 times 3, 0, 7, 8? What would that be? We get 30, 0, 70, 80. It's more interesting if we factor, right? What if I've got the matrix that's like a row vector, 200 minus 1,000, 300. We tend to use scalar multiplication in reverse more, as it actually happens, right? Like, it's really more interesting in terms of doing something like, oh, I can factor out 100, right? And then this is 100 times 2 minus 10, 3, right? It might be nicer to work with 2 minus 10, 3 for the purpose of some question as opposed to 200 minus 1,000, 300, right? All right. So I don't think I've ever had a 221 class that got confused about any of this. This part is just like, yeah, okay, whatever. But what we're about to do, matrix multiplication, well, that starts to get interesting. So, definition, if we have A in R m by n and B in R n by p, all right? So basically, we have like an m by n, and B is an n by p. You notice that we have matching, these are matching. See that? These have to be matching. If that's the case, then we define AB to be an element of our m by p, m as in mommy, p as in, penguin, I guess. I don't know. So then AB, the ijth element of that is by definition the sum k equals 1 to n of a I k b k j. That is a stone cold formula, a definition for matrix multiplication in a lot of cases. You guys know about dot products? Like if I have two vectors and they're both n-dimensional, let's just throw it out here. If I have like a vector v, which is, like v1, vn, and if I have a vector w, which is like w1, wn, and I'm purposefully using a different notation because I want to think of these, they could be rows and columns or they could be columns and rows. The point is you've got a collection of n things, all right? If that's the case, you can talk about the dot product of these guys. And that gives you a number, and it's just defined to be like v1, w1, vn, wn. Or if you like, in the other notation, sum k equals 1 to n of vk, wk, all right? So as you look at this definition I just wrote down, if you want to, we can reverse engineer this into a dot product of something. Let's think back to the thing I just erased. Poor planning on my part, right? I just erased our definition of row and column, didn't I? So you guys are going to have to help me out. Sorry to the people at home. I didn't do too much yet, though. Like, what's AIK? That's row I, the kth component, right? This is row I of A, the kth component. What's BKJ? Is that not column J of B, the kth component? Right? So it's matching components of the row of the left and the column of the right in the product. But that's a dot product. See, that's nothing more than the dot product of the ith row with the jth column. So this, as a matter of calculation, is a pretty nice way to look at matrix multiplication. It's just taking a bunch of dot products of rows of the left thing with columns of the right thing. All right? Let me show you like a specific example of this. We'll keep it 2 by 2, so we don't have to write too much to start with, at least. All right? If I can find a marker. I need to find some more blue markers. We're running low on the blue. What example am I on? 4? All right, so what if I do, like, let us say 0, 1, 1, 0 times the matrix 1, 2, 3, 4. Can we even calculate this product? Does it make sense? Notice that we've got is a 2 by 2 times a 2 by 2. So there's hope, because the 2's, they be matching, right? And then, so this means that the answer is, again, a 2 by 2 matrix, right? All right, so let's do it. I'll try to do some color coding. So I need to do the dot product of this and that. That's my first thing. So I've got, I'll write the other notation, like 0, 1 dotted with 1, 3. We've also got this with that. So that goes over here. I get 0, 1, first row dotted with the second column to get the 1, 2 component. All right. Second row with the first column. So that gives me 1, 0 dotted with 1, 3. And then finally, we have the second row dot product with the second column, which gives me, again, 1, 0 dotted with 2, 4. Okay, so how does that work out? This is 0 plus 3, 0 plus 4, 1 plus 0, 2 plus 0, and what we get in total here is 3, 1, 4, 2. Can you tell me a story of what happened here with this matrix? What happened here? If I think of this matrix, let me give it a name. If I think of this matrix as A, what happens with what's the answer? It's like we took what? We took row 1 of A and we made it into row 2 of the answer. And we did what? We took row 2 of A, yeah.
Is it because that's kind of like a reverse identity matrix?
Yes, in fact, you're right.
Because if it wasn't identity matrix, it would just be the same thing.
So if you're right, you're suggesting that whatever we do to the identity matrix. Well, no, you're fine. So if I take the identity matrix, whatever that is, we don't know that. That must be. Are you a time traveler? You're from the future, aren't you?
I learned it in pre-calc.
Oh, pre-calc. What? Pre-calc?
Yeah, I don't know why.
Wait a minute. Who taught it? Here?
No, not here.
Oh, man.
Back in my high school.
I want that to be here. Like, that would be.
I don't know why they taught it that. Like, I didn't really understand it well.
I mean, I'm impressed. Like, that's a good teacher. I have done matrices in college algebra here once I taught it. They did not like that. I also did the, like finding the, converting, how do you convert like an unending decimal representation to a fraction using the geometric series? I also did that in college algebra once, but just once.
I mean, matrices are
Just
on
once.
the SAT.
Oh, on the, yeah, honestly, like, this stuff isn't bad. Everything we've done up to this point, Dr. Sprano did in high school. And it wasn't a matter of like having an odd teacher, it was just standard curriculum. So, because really what I showed you last week is the way to solve equations. It's way, way more efficient than the elimination method. And as such, it's something everybody should know. Because we all find ourselves tasked with the problem of, solving linear equations. They're everywhere. What you're saying about why this happened is actually very interesting. Although this does get ahead of the story a bit, so I better not. Let me just say that this example is what just happened. There's more to say there. Well, okay, so we'll get back to this example by the end of today, hopefully. All right. I need a bunch of toys before I can explain. Example 5. We should do another one. Suppose I have like 1, 2, 3, 4, 5, 6, and I'm multiplying by 1, 1, 1, and 0, 0, 7. All right, can I form such a product? Is it allowed? So notice that this is a 2 by 3 times a what? 3 by 2. So the answer is yes, we can. So what we do is we do 1 times 1 plus 2 times 1 plus 3 times 1. What's this cross I'm writing in the middle? Is that part of the matrix? It's just a means of making sure you understand which goes with which, right? Because if we don't have any, if we just have white space between the numbers, they can bleed together. So I just put crosses in as a means of organizing the calculation. It's just a bookkeeping device. Of course, here we have 4 times 1 plus 5 times 1 plus 6 times 1, right? So again, dot product of first row with first column, dot product of second row with first column. And then we've got 1 times 0 plus 1 times, my bad, 2 times 0. It wouldn't have been wrong. Plus 3 times 7. And 4 times 0. 5 times 0, 6 times 7. Or you could say 6, 7. And why are you snickering? Let's see here. Seems kind of dumb that you're snickering. A little bit dumb. I have children. So let's see here. 3, 6. 15? I think, is that 15, right? And what do we get here? 21 and 42. There you go. If this is A, right, and this is B, what happens if we look at B times A? Can we do that? Does that even make sense? So we'd have a 3 by 2 times a 2 by 3. Yeah, it would make sense. But now the product in reverse order is not even the same size. It would be a 3 by 3 matrix. And I'll write that out. Let's see here. you guys will forgive me. I'm going to start just writing the answer down because writing out the steps is annoying. 1, 1, 11, 2, 2, 2 plus 35 is 37, I think. 3, 3, 3 plus 42, 45, okay. So there you go, that's BA, and obviously it's not equal to AB, right? And you might say, well, that's just because they're not the same size, right? Well, let's circle back to example 4, and let's try example 4 tilde. Let's try 1, 2, 3, 4 times, according to the time traveler, the messed up identity matrix, whatever that is. I will define the identity matrix before long, so it's fine. But have you guys seen Fringe? No? Oh, I don't know. It's just the greatest science fiction show of all time, so whatever, don't watch it. Let's see here. So, ignoring the 4th and unfortunately rushed final season, thank you, Fox. But so if I do this multiplication, I get 2, 4 and 1, 3. Yep.
1 plus 7 times 4 is 10.
What did I do? 1 plus 1 plus 4 times 7 is not 11? Yeah, I think you got a point there. So you want to trade that 11 in for something that... See, I make that mistake on purpose so you guys are paying attention. So you're welcome. Yeah, if you see something, say something. That 11 is bogus. That's the unfortunate, side effect of not writing down steps. So we have 1 times 1 plus 4 times 7, also known as 1 plus 28. I believe we're looking at a 29, truth be told. Any other mistakes? If you're not as fast as me at multiplying matrices, that's okay. Keep in mind, point of order, I've done nothing but math my entire adult life. I would hope I'm faster than you if I'm awake. Although you're young, so you'll beat me eventually. Can you guys tell me what the pattern is here? We agreed that the other one, we flipped. When we multiplied this way, we juxtapose rows 1 and 2. What happened now? We've done what? Looks like we've swapped columns this time. That's kind of neat, right? I can explain this to you as part of like a larger theorem that's worth knowing. And so here's a little theorem. The column by column rule. And here's how that goes. If we have A times B, all right, and we write that as A times like B1, B2, B. How many columns does B have? In my setup, B had P columns, right? Great. Then the rule is simply this. That's AB1, AB2, ABP. So like we can, instead of multiplying the matrix as on the left-hand side, we can instead multiply each column on its lonesome. Now, of course, this begs the question, how do we multiply a matrix in a column? I guess maybe I haven't defined that yet, right? How should we define matrix column multiplication? What does that even mean? So my bad. This is a little bit out of order here. I guess probably I should define these first, right? How to define. So before I even define it, let me show you an example of how it works. You'll forgive me if I do that. It's probably what you want anyway. So if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and I multiply that by the column vector x, y, z, how does that work? Does that make sense? I would argue it does make sense. This is 3 by 3 times a 3 by 1, so we expect the answer is a 3 by 1, also known as a column vector, right? And so it's just dot products again, guys. So what you do is you take this dotted with that. That's the first component. So like x plus 2y plus 3z. Then you take that column, dot the second row for the second component, which gives us 4x plus 5y plus 6z, right? And then you see, you take the dot product of the third row with the column, and you get 7x plus 8y plus 9z. Right. So this is how we multiply a matrix by a column. If you want, I can give you the general definition. Here's how that goes. Ax, I forget if I want I guess I want the ith component of it, should be equal to the sum j equals 1 to n of a, I, j, x, j, I believe. So here, for a, an element of R m by n, and x, an element of Rn. I should probably double check the formula, just make sure I haven't, like the only danger really is that I should have the I and J swapped or something. No, actually it has to be this. All right, so that's the so this is a special case, right, of the definition we had over there. Notice there's two indices because the multiplication gives you an honest goodness matrix which has rows and columns. So you need two indices to index a matrix with rows and columns, right? But if we just have a column, one index suffices to label it, right? And this is how we do a matrix column product. There's a few other weird cases we should talk about that'll catch you off guard if you don't know about them. Let's see here. So, example 6. We could do something like 1, 2, 3 times, say, 4, 1, 1, 0, 1, 1, for instance. So this is a row, this is a 1 by 3, right? Times a 3 by 2, so we expect the answer is a 1 by 2, right? So the way that works is we do, 1 times 4 plus 2 times 1 plus 3 times 1, comma, 0 times 1 plus 2 times 1 plus 3 times 1, which of course is whatever that is, 6, 9, 5, right? So this is a row times a matrix gives us another row. I hope you're starting to pick up on the fact that it matters very much whether the product is on the left or the right. We can't just commute letters. It doesn't even make sense. All right. Even when it does make sense to commute the letters, it turns out that we've already seen it, right? If you look back at example 4 and example 4 tilde, notice that 1, 2, 3, 4 times 0, 1, 0, 1, 0 is not equal to 0, 1, 1, 0 times 1, 2, 3, 4, right? Matrix multiplication does not commute. All right, so what's the definition for row column multiplication? I'm trying to show you guys all the weird cases all at once here just to try to group them together in one spot for you. I mean, every one of these weird things we use somewhere, so it's not like just, you know, fool's errand to talk about them. But here, if I have, let's say, y times a, the jth component of that, that's going to be equal to the sum I equals 1 to m of, excuse me, y sub I, a sub I, j, for y an element of R 1 by m, and a m by m, m by n, m as in mommy, n as in nenu matrix. So there you go. So that's the definition of row matrix multiplication. All right. Let's see if I can think of the other weird case. We can also just do 1, 2, 3, 4, 5, 6 like this, right? This is what? 4 plus 10 plus 18, also known as 32. So a row column product is what? What is a row column product? It's a scalar, right? So if I was to say that the vector v is 1, 2, 3, right, and the vector w is 4, 5, 6, then v dot w I could write as v transpose times w, with the meaning v transpose would be the vector 1, 2, 3 like this, and w is 4, 5, 6. All right, so dot product can be rewritten, the dot product of two column vectors can be written as transpose times the other, right? How about this? What if we did the other way around? What if I did 4, 5, 6 times 1, 2, 3? Would that even make sense? Check it out, right? 3 by 1 times 1 by 3. It does make sense. But what is it? What is the matrix? It's a 3 by 3. What are its entries? So, yeah, so what it is you do 4, 5, 6 in the first, you do 8, 10, 12 in the second column, and you do 12, 15, 18 in the third column. So all that it does is it multiplies the left factor by the components in the right factor. Just that's how this works. In this particular context, like you could talk about it, if I have v, I'm talking about like, you know, v is a column vector and r is a row vector, let's say, and you're talking about the ijth component of that, well, it's just equal to VIRJ, I think. So like here, if this is my V and this is my R, this 4 is, you know, VR11, which is, by the way, V1 times R1. This is actually a special case of the definition where the summation over the k is gone. There's no need for the summation in the definition on the left-hand board because there's no middle index to sum over it. So the summation in our original definition there is gone. All right. I think I'm fresh out of matrix. I think I'm fresh out of weird cases to show you guys. So let me finally define the standard matrix, the standard basis. So here's how that goes. EI, the jth component, it's equal to 1 if, well, let me say this more civilized. So EI, the jth component, is Kronecker delta ij. You might wonder, what's Kronecker delta ij? Well, it's 1 if I is equal to j. It's 0 if I is not equal to j. So this defines the so-called the ith standard basis in, let's say, Rn. Now this notation is, what's the word? So like example 9, R2. What is it?
What did you write when you said definition EIJ equals what?
Is it, this is Kronecker delta ij, so it's a delta with an I sub j.
Okay.
And that's just a notation for this case-wise thing. Like it's 1 if I is equal to j and it's 0 otherwise. So for example, in R2, you have E1 is 1, 0. E2 is 0, 1. But if we're talking about R3, we'd have E1 is 1, 0, 0. E2 is 0, 1, 0. E3 is 0, 0, 1. So like this notation has to be understood in context. But like what E sub I is it's a vector, a column vector, where only one thing is non-zero, and that's whatever its label is. So like E1 has a non-zero entry in the first component. E2 has a non-zero entry in the second component, but nowhere else. All right. So do you guys, we have a different notation for these in Calc 3 if you've had Calc 3. What is it? Do you know? Are you taking out Calc 3 right now, or?
I already took it.
Already took it? So, not with me, right? Okay, that would be embarrassing. So E1, E2, E3 in Calc 3, we use IJK for there, right? These are the unit vectors that just go one in the first direction, one in the second direction, one in the third direction.
So they're just equivalent.
Yeah, they're equivalent to IJK, but we use the notation E sub I so that we're good for 2 or 3 or 20 vectors, whatever. Like it's, we got it covered. So let me show you some things we can do with those. So one of the things we can do with those is if I have X is in Rn, right? I can write X as X1, X2, Xn, right? And if you follow the definition of matrix multiplication and matrix addition, and you let those definitions apply to vectors just the same, then what happens is we can pull X1 out and write it times this. And we can pull the X2 out and write that. And we can pull Xn out and write this. If you don't believe me, it should be fair enough. It should be clear enough that if I took these and brought the scalar multiple outside in, we'd still have 0, 0, da 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 0, xn, right? 0, x2, 0, 0, 0, 0, 0, right? x1, 0, 0, 0, 0. And if you add those together, we get back here. All right? But what is this? This, by definition, is E1. This, by definition, is E2. This, by definition, is En. So what I'm showing you is that we can build any vector x as the sum, you see, I equals 1 to n of x sub I, E sub I. We can build any column vector like this. That's why it's called the standard basis. You can build any vector with the standard basis like this, and uniquely so. If you tell me x1 through xn, you have specified x uniquely. All right? Okay. A natural question to ask, what happens when we multiply a matrix by the standard basis? All right? Like what happens if I take, say, A times, like E sub I. Well, it turns out that this works out to the ith column of A. A times EI is the ith column of A. And by the way, if we take, say, maybe use a J here, because I've been using J for columns more. It doesn't really matter. The notation's not reserved, right? Every place I've used I today, I could use J if I was consistently so, all right? The letters I and J are not reserved exclusively as rows and columns. You can already see that in the definition of transpose, right? It would be impossible to define transpose if we insisted on I always being the row index. Okay, anyway, so EI transpose times A, guess what? That's row I of A. All right? Now I could prove these, but I don't think you guys really want me to. But it's a straightforward matter of chasing down our definitions and working out how it works. Let me show you why this is useful. If we go back to my example 4, we can see it in a new light. See? What we have when we look at 0, 1, 1, 0. Actually, let me do example 4 tilde to start with. So we had 1, 2, 3, 4 times 0, 1, 1, 0, right? Revisiting it. In other words, what I have is I have 1, 2, 3, 4 times, well, that's E2, and that's E1. Do you guys see that? All right. But I told you a theorem over there that I never proved, but proof is in the notes. It's not really complicated. I've made it homework in this class before. The column by column rule. My claim is that this matrix product is the same as 1, 2, 3, 4 times E2, concatenated with 1, 2, 3, 4 times E1, which is what? Column 2 of 1, 2, 3, 4, column 1 of 1, 2, 3, 4, which is what we found by the definition of matrix multiplication, right? 2, 4 for the first column, 1, 3 for the second column. Guess what? There's also a row by row multiplication rule as well. So like the row by row multiplication rule, oh, I shouldn't erase that. I regret that if I do that. So what's the row by row multiplication rule? Well, if we had A is like a stack of rows, A1, A2, you got M of them, right? Stack of rows times B, that is actually equal to A1 times B, A2 times B, AM times B. I hope you see the difference. The column by column rule presumes that we have a concatenation of columns on the right, so we can factor the matrix in like that by matrix multiplication. If we have a bunch of rows over here, we can bring it in like that from the left. But there's asymmetry in the process here. Left and right are different. So if you use this rule on my example 4, revisited, if we look at 0, 1, 1, 0 times the matrix 1, 2, 3, 4, I can look at that as, well, that's E2 transpose, that's E1 transpose, right? Times 1, 2, 3, 4, which allegedly is E2 transpose times the matrix 1, 2, 3, 4. I really should have invented a letter for that matrix rather than keep writing it, but oh well. E1 transpose times 1, 2, 3, 4. But by the way, if you multiply the transpose of the standard matrix on the left of a matrix, you pick off the row rule. This gives me row 2 of 1, 2, 3, 4, and row 1 of 1, 2, 3, 4, which of course is what we found, right? Right? I think I've erased it now, but you guys still have it, right? So I'm telling you, like, you definitely want to memorize this one right here, especially, is very, very helpful for certain matrix calculations because it's such a simple thing to just copy down a column, right? You don't actually have to think about the matrix multiplication. Let me actually like put that into practice here. What am I on, example 8? I don't know. Let's say 10. All right, so if I've got, 4, 5, 6, 7, 7, 7, 8, 8, 8, for instance, right? And I multiply this by, 1, 0, 0, 0, 1, 0, 0, 0, 1. So first of all, let's not write all these numbers again. Let's invent a letter here. So I'm going to call this A. All right. What is this? This is E1, E2, E3 in 3 dimensions, right? So by the column by column rule, this is equal to, well, AE1, AE2, AE3. Wait a minute. So this is column 1 of A. Column 2 of A. Column 3 of A. I think I never moved the camera. What is that?
A.
A. Or A. If you want to give it more of a Happy Days accent. But yeah, it's A again. And so this is that matrix that the time traveler brought into the lecture a while ago. This is the I3, the 3 by 3 identity matrix. Right. Let me suggest that we can make the identity matrix by concatenating the standard basis into a square matrix. Let's define that. I'm going to erase this. So, definition. IN is E1, E2, ... En. So this is, an n by n matrix. The n by n identity matrix. What happens if we take this matrix, right, times A? We get A again. And why is that? Because, oh man, I want to do that where I messed it up, guys. I'm sorry. I meant to do A times that. Because then this is AE1, AE2, right? AEN, which by the way is column 1 of A, column N of A, as you guys told me a second ago, A. What if I put the I on the other side? What goes on then? What is IN? A. Notice what that is, E1 transpose, all the way down to EN transpose, isn't it?